Okay. So, in the 4 families of methods to solve constraint optimization problems, we have covered 2 penalty methods, making the main search in the space of x variable, the primal variables. The second one was primal methods, in which the main search is made in the feasible space, which means a space of n minus m dimensions, where n is the number of variables design space and m is the number of active constraints. Now, we are in the third family of methods, which are the dual methods, which make the search in the primary search in the space of the Lagrange multipliers, that means m dimensional space, if m constraints are active. Now, the philosophy of this family of methods is that in a constraint optimization problem, the main defining features of the solutions of the optimization problem, that is of the minimal points, basically lie in the geometry of the Lagrange multipliers, and therefore, finding the correct values of the Lagrange multipliers is primary to the solution process. Now, how do we go about it? So, we go to the dual methods. Now, before I start with the methods, I will first remind you about the concept and idea of local duality. Basically, I will summarize what we have covered some time back. First of all, the basic assumption of local duality or Lagrangian duality is that the objective function, well, not really the objective function, the Lagrangian. Okay. This should be the Lagrangian. The Lagrangian function is convex at the minimum point. This is actually not necessary so far as the second order necessary conditions are concerned. According to the necessary conditions, only this much is necessary, that the Lagrangian should be convex in the tangent subspace of the constraints, active constraints. Okay. So, this matrix at the minimum point should be such that it behaves in a positive definite fashion for any vector in the tangent subspace of the active constraints. That is what is required. Okay, that is what is necessary, second order necessary condition. Now, the assumption of local duality is the extra facility or extra gift that the Lagrangian function is convex overall, that is in other directions also, in the normal directions as well. Okay. So, that means the Hessian is positive definite completely, okay, not only in the tangent subspace. This is the assumption. Okay. Now, with this assumption the local duality works, and now here we will see how the local duality really works and how it can be made to work if this assumption does not hold. Okay. So, first of all, the Lagrange multipliers corresponding to the minimum point are denoted as lambda star mu star, not simply lambda mu, because lambda mu will be variables now, and lambda star mu star will be one set of values for those variables. Now, the consequence of this assumption is that x star is also a local minimum point of this function. Now, what is this function? This is the Lagrangian function with the values, the correct values of Lagrange multipliers provided. X is left as variable. So, this is a function and this is a function of x. So, Lagrangian is a function of x lambda mu, in that for lambda and mu, when you put the lambda star mu star correct values, which for an algorithm to begin with you do not know, but if you knew from somewhere and if you put that, then the function that you get in hand, that is what we are right now calling as f bar. And you can check very easily that if this is positive definite, that is positive definite in all directions, then x star is a local minimum point of this also. Obviously, because for the correct values lambda star mu star, this is positive definite. This fellow's second derivative Hessian is positive definite, and its first order derivative will obviously satisfy the KKT conditions. So, it will be a minimum point, x star will be a minimum point of this function. Now, around this point x star, if we around this point lambda star mu star, if we vary lambda mu, then we get this. Okay. So, varying lambda mu around this reference value, say, we get this Lagrangian function which we know about, and then we say that when we try to minimize this, then if we have given the lambda star mu star correct values, then we get the local minimum point correct value x star. If we give lambda star mu star a little different value, then we get a little away, the corresponding x star value for the wrong value of lambda mu will come a little away. We vary lambda mu a little more, it will come further away or in some other direction. Okay. So, that means that every time this so called minimum point that we get will come as a result of the prescription of lambda and mu, right. So, that way this x that we define for different values of lambda mu, that can be considered as a function of lambda mu, and that function we call as the minimizer corresponding to this prescribed lambda mu value. And this function, the minimizer, we will denote as x of lambda mu, because according to our prescription of the Lagrange multiplier values, perhaps away from the correct ones, we get different minimizers. Okay. And then when we insert the lambda mu that we have given along with this x of lambda mu in this function description, rather in this function description in the Lagrangian, we get a function of lambda mu only, and that is dual. So, in the neighborhood of lambda star mu star, we define the dual function in this manner. As function of lambda mu, we get hold of the minimizer x, and then that x and that lambda mu as we put, we get the Lagrangian, and this is how we define the dual function as a function of lambda and mu, which is the minimizer of the Lagrangian in terms of x only. Okay. Lambda mu we prescribe, we get the value, and that is the dual, that is this function of lambda mu. Since the definition itself of the dual function is dependent on a minimizing action with respect to the primal variable, that is why we say that feasibility definition of the dual itself is directly related to the optimality of the primal, minimality in particular. Okay. And then when we were studying duality, we saw that its derivative with respect to lambda mu turns out to be this, that is h and this g basically. Okay. So, that means if the point so far as x is concerned is feasible, that is this is 0 and similarly this is 0, that will mean that this is 0 and this is 0, and that is the first order condition for the optimality of the dual function phi, right. So, here we find that optimality of the dual is feasibility of the primal. These two things work together to ensure that if you make the dual feasible as well as primal as well as optimal, then from here and here you get both for the primal also. If you do both on the primal side, then also you get both on the dual side. Again, you can, if you do only optimality of the primal, on the other side optimality of the dual for the same x lambda mu, if you ensure, then the feasibilities are guaranteed on their own. So, that means out of these 4 you can make pair like this, or pair like this or pair like this, and any two pairs you satisfy, the other pair automatically gets satisfied, and that is the part and parcel of dual method. Okay. Further, so going into the second order condition, we have earlier discussed that the Hessian of the dual is negative definite everywhere. Okay. So, the dual function is concave everywhere, in particular at the optimal point also, in particular at that point also where these two are 0. Okay. And therefore, wherever these first order conditions for the dual optimality is satisfied, the point gives you a maximum point of the dual function, because the dual function is concave, its Hessian is negative definite everywhere. This we have shown earlier and we have satisfied ourselves. So, the strategy for the dual method is to maximize the dual function. Define the dual, of course, through a minimality of the primal on the way here, and then say that this dual we have defined, we are going to maximize religiously. By the time we reach that maximum, the corresponding point gives us the minimum of the original function, that means the solution of the primal problem. So far so good, this is local duality. Now, what if the function f x is not convex at x star, not function f x, but a Lagrangian. Okay. What if the Lagrangian is not convex at x star? It is convex only on the tangent subspace as required. Okay. So, satisfying nothing beyond what is necessary. Then what? And we will see that. Before that, we see two other things. So, in dual methods, we will see three things. First, we will see as it is how we can apply local duality in problems with a particularly marked advantage. To begin with, dual methods can be applied to any optimization problem wherever you can define the dual in a civilized manner. In particular, in a particular class of problems, the so called separable problems, dual methods give you a large advantage. And what is this separable problem? A separable problem is one in which all the primal variables, all the variables of the problem, you can partition into several small segments, such that the objective function as well as each constraint function can be defined as a contributed sum of individual functions of those little segments of these partitioned sets. That is, one f 1 is there, which is a function of x 1 only, that is this bunch only participating there. Another f 2, which is function of x 2 only, and so on. And the objective function happens to be a sum of these f 1, f 2, f 3, f 4. If this kind of a partitioning of the variables such that induces a partitioning of the objective function as well as each constraint function, then such a problem is a separable problem. So, a separable problem is characterized with this kind of a structure. In this kind of a structure, what will be the advantage? You will see that the Lagrangian will be simply sum of this sigma plus lambda transpose this sigma plus mu transpose this sigma, that will be the Lagrangian. And then you find that the sigmas, the three sigmas are operating over the same I, the same index, and therefore, you can take the sigma common out and put it like this, and inside for I equal to say 3 when you put, then this whole thing is dependent on only x 3 and not x 1, x 2, x 4, etc. Now, x 3 can be a little bunch of variables, it is not necessary that it has to be a single one. If it is a single one, it is best, it is greatest. Okay? The advantage is best more, the advantage is highest. Okay? Even otherwise, if there are 20 variables and you have a bunch of 3 which define something together and another bunch of 2 which define something together and so on, like this, if you break down the entire 20 variable problem into 4 bunches or 7 bunches, each having 2, 3, 4 variables only, then that is an advantage. Okay. So, now when you minimize this, you say fine. So, I am going to minimize this whole thing. So, in particular, if I minimize each of the components in the sum, then the total is certainly minimized. So, put the min inside the sigma, and that can be done because this depends only on I, no other index. Okay. And one such minimum with respect to x I will give you the corresponding dual, call it phi I, and lambda mu, the Lagrange multipliers are common. Okay. So, now the dual function turns out to be a contributed sum of individual duals. Okay. And while defining this, you see the actual minimization was done not on the 20 variable problem, but on small 2 variable, 3 variable, 4 variable problems. Okay. This is the advantage, that is the actual hard work in defining the dual, because in dual methods the actual hard work is in defining the dual. Okay. That is the main minimization problem involved. Okay. So, that is done over a much smaller space. Okay. Now, this was not possible if you had used an ordinary primal kind of method, because there you could not say that I will minimize each of them separately and then sum them up. That will indeed be a minimum, but the point is that it is also possible that the function is minimum where none of them is minimum. One of them is going lower, another is going higher, and in between somewhere it happens that the sum turns out to be lowest. So, when the sum turns out to be lowest, each of them does not have to be the lowest, some of them will be, okay. Some of them might be. So, one component decreases so much that it can handle the relatively higher component of the other also. Okay. So, such a minimum point also will be captured like this. So, this is the method of the dual strategy anyway, but in the case of separable problem, this is the advantage, that is actual minimization is done in a split manner over smaller subspaces, and the formal problem is defined as maximize this dual function. Okay. So, you recognize a separable problem by contributed parts by the primal variables, okay, in the objective as well as constraint functions, and such problems are ideal for dual methods. In the assignments, you will find one such problem, and I advise you to do that quite seriously and see how it works in assignment 11. Yeah, this fifth question of assignment 11, this suspended chain problem. Here you will see that the objective function as well as the constraint functions are all contributed parts. Okay. So, this will operate very well by a local duality itself. Okay. Now, we come back here and see what else we have. Another method which is called cutting plane method, it is a beautiful method. Unfortunately, it is applicable only on a subclass of problems. Okay. So, in this, objective function is linear and the domain is convex. You remember what is the definition of the convex function? I mean, what is the definition of a convex programming problem? A convex objective function in a convex domain. So, this is certainly a convex optimization problem, convex programming problem, but even in convex programming problem, this is special, because objective function is not only convex, it is linear, okay, and the domain is convex. So, it is a special class of convex programming problem. So, you say this in this manner, minimize f x equal to C transpose x. So, a linear objective function and plus constant, whether you give or not, it does not matter either way, subject to x belonging to a domain. Okay. So, this domain S is designated with inequality constraints in which each of these g i's is a convex function. Okay. Now, how does cutting plane method work? It first selects an initial polytope. You remember what is polytope? We discussed what is a polytope at length earlier. So, I remind you that whatever is a polygon in the 2D space, that is a plane, what is a polyhedron in 3D space, that is this ordinary space in which we live. A corresponding thing in the multidimensional space, n dimensional space, is called a polytope. Okay. So, solid region in that space bounded by, I mean it does not have to be bounded from all directions, all sides, but if any boundary is there, then that boundary is linear, that is planar. Okay. So, that kind of a thing is a polytope. Now, select an initial polytope, say call that polytope as z naught, such that the entire domain of our problem is a proper subset of z 0, is safely inside. And how to select such a z 0? It is actually very simple. You can define it just like this: z 0 is the set of those x's which fall between x l to x u. Okay. So, that means this is a vector, this is a vector. Okay. So, for every variable x xi, you select an xil lower limit and an upper limit. Basically, this is a rectangular polytope. Okay. So, like this, and like this, if you make a cuboid, that is a rectangular polytope, a polytope of this kind. Okay. So, big ones, big limits you take, so that the entire domain is safely enclosed inside that. Okay. So, for example, let us take this, say this is one constraint. Okay. This is another constraint. This is another constraint. This is another constraint, and this is another constraint. The domain that I have enclosed, that is obviously convex, right, because each of the boundary parts that I have drawn, that is convex. Now, to enclose it with a polytope of that kind that we discussed, you basically say that I put an x 1 greater than or equal to this, and x 1 less than or equal to this, x 2 greater than or equal to this, x 2 less than or equal to this, and this rectangle is a polytope which safely encloses this. The actual domain of the problem is a clear boundary of that. Okay. So, you define that, and then what do you do? So, the requirement says that such that the linear objective function is bounded below in z 0. If you define z 0 like this, if you define the initial polytope like this, then any linear function will be bounded below in that, because it is closed. Okay. So, it is closed from all sides. So, it will be anyway bounded. So, this polytope that we have defined, the rectangular polytope, in that any linear function will be bounded, certainly there is no problem. Okay. Now, we solve the, now from here the iteration starts, set k equal to 0, and then solve the linear programming problem. This is the linear programming sub problem. Minimize the objective function subject to x in this polytope, okay, z k. So, initially we have defined z 0 and we have set k equal to 0 to begin with. So, this becomes this z 0 rectangular polytope, and as you minimize this linear programming problem, suppose the result is x k. So, in this particular case, suppose the minimum point turns out to be this. Okay. Fine. Now, what to do? The next step says first of all check whether it is feasible or not. Okay. If it is feasible, that means you have converged, that means stop. If it is not feasible, in this example you find that it is not feasible. So, identify M such that this is G M x k is max, that is at this point which constraint is violated most. If it is not feasible, then that some of the constraints will be violated, and whichever is the most violated, identify that. So, suppose in this case we say that well, this one is satisfied perhaps, okay. This one is satisfied, this one is satisfied, these two are certainly violated by this point, okay. These two. Okay. So, suppose this one is most violated, this one is most violated, this is a culprit, this is a culprit first round. So, this is the most violated. Okay. So, then now is the basic operation of this method. After identifying which one is violated, G M, that is M, define a cutting plane. Okay. P k x is equal to G M x k plus this, like this. Okay. Define this. Now, this is something. We started with the understanding that every G is convex function, because the domain is convex. So, that means this G M x k plus grad G M x k transpose x minus x k is basically the first order approximation of G M around x k. This is a first order Taylor approximation. G M evaluated at x k plus grad G M transpose into x minus x k. Okay. So, this is a first order approximation, first order Taylor approximation of G M around x k. So, this thing equal to 0 is the cutting plane. Okay. Now, first order approximation of a convex function is typically lower, why typically always lower or equal compared to the true function value. Okay. So, whatever you do like this, there the function value that is anywhere other than x k, the actual function value of G M will be higher and this estimate will be lower. Now, suppose you say that I am plotting this equal to 0. So, this equal to 0 is a plane, because this is a linear equation in x. You see, this is constant, this is constant, and this is x minus x k. Okay. So, it is like a plus b times x minus x naught. Okay. So, it is a linear equation. So, it defines a plane. So, it will define a plane like this. Okay. And on this plane, what value of G M you expect? On this plane, at every point you find that this expression is 0, this expression is 0. That means, the first order Taylor approximation of G M anywhere on this plane is 0, and the actual value of that will certainly be higher. Okay. So, at every point on this plane G M is positive. That means, not only this point is infeasible, this entire plane is infeasible. Okay. And at every point in the domain G M is less than 0. Okay. So, that way this plane separates this side from the original polytope, okay, or from the original polytope, this side of that it separates, and the entire domain of the original problem, actual problem, remains on this side. Okay. So, this plane basically is a cutting plane that cuts off one half space, which includes this infeasible point. Basically, the domain becomes a little smaller. Okay. Now, you say that what we will now do, we will define this as the domain. This this, basically one corner of the earlier polytope you have cut off. Okay. And how do you define that? You say that with this cutting plane we separate this currently infeasible point which has been found as the minimum point for the time being and the actual domain and this half space. So, when we take the intersection between these two, the original z k and this half space which is OK, where this is lower. Okay. So, at x k this is positive and on anywhere in this plane, this equal to 0 plane, this p k is 0 and on the domain side it will be negative. So, when we take this intersection we get this polytope that I have shown you here, okay, this polytope. So, now with this new polytope defined as z k plus 1, you solve the linear programming subproblem again. Now, the domain is a little shorter than last time. And now, in this round perhaps you will find the minimum at this vertex, say, fine. Now, again this will be perhaps the worst violator and now perhaps the cutting plane will turn out to be like this and this time in the next iteration perhaps it will be here and this time maybe it is the other one which is violated most, that is this one which is violated most and so the cutting plane may be like this and you see by now the domain has become this and like this you go on redefining the polytope, shortening it from this offending side and going on solving the linear programming problems, okay, and make it like this. Finally, you will come perhaps the corner of the polytope will approach the, this is unlikely to happen or maybe no, it will not happen because I mean because here actually this is the solution or something like that. So, as you go on defining more and more cutting planes and reduce the polytope slowly on that side, then slowly the minimum that you get at every round here will approach the domain. At every iteration you are handling a minimum point, okay, when you solve this linear programming subproblem. The only problem was this feasibility check. The moment the feasibility check satisfies, okay, the moment the feasibility check holds, that is it is found feasible, you have got your solution. Okay. Now, where is dual in this? Duality in this method, in the cutting plane method, is in the interpretation. You see, in the dual problem, the main problem defined is to maximize the dual and therefore, at every main iteration the new set of lambda mu gets defined and the objective function increases, increasing. When it does not increase anymore, you have got the maximum. Okay. That is how the dual is maximized and correspondingly the primal objective gets minimized at that point with the satisfaction of the constraints also. Now, here also you see, compared to every minimum point found in one iteration, in the next iteration the minimum point found, the minimum value found, this one actually increases, because certainly in the first round this was not the minimum point, because then this would not be found, because this was also part of the domain. Only when this part was cut off by this cutting plane, then this was found as the minimum. So, this is certainly larger than this. So, at every new iteration the so called minimum point actually goes on increasing, thereby basically improving feasibility. Okay. So, it looks as if over the iterations we are maximizing something. Compared to f x 0, f x 1 is higher, compared to that f x 2 is higher and so on. And then when this converges, it does not go any higher anymore over next iterations if we conduct, then we say that we have converged, that is the maximum of this sequence. Okay. And that is the feasible minimum point that we were looking for. And all the points in this sequence have the basic disease that they were infeasible, okay, except the limit. At the limit, we have got a feasible point finally, and that is how a typical dual method also works. And in a typical dual method, at every iteration, the definition of the dual itself ensures that we have already done a minimization, okay, because through the minimization of the Lagrangian, we basically define the dual. So, minimality of, in this case also you find that minimality of the function was granted at each step, because of the very mechanism of the method. Iterations basically improve feasibility. That is what a typical dual method also does. So, its spirit, the cutting plane method's spirit is in duality. Okay. So, we stop here at this point, and the major method of the dual category, augmented Lagrangian method, that we discuss in the next lecture. Okay.